Newton's spring law worked beautifully, but push on while a spring pulls back, and the answer keeps retreating into the metal, into its atoms, into the charges and the quantum rules that bind them. To truly explain any force, physics hunts for a small set of fundamental forces. Today we meet the first, gravity. A force law is a mathematical model built from observation, and every model has limits. Hooke's law fit the springs we tested, but does it hold for every spring? Each one has its own range of linear behavior, so the law still isn't truly universal. To trust it, we want some property shared by all springs that produces the force. Picture a spring as countless tiny pieces that snap back together when pulled apart. What supplies that pull? Follow it down. The steel is a lattice of atoms. The lattice holds because of the electrons that bond neighboring atoms. Those electrons carry charge, governed by Coulomb's law and the rules of quantum mechanics. Explaining one ordinary spring drives us all the way down to the fundamental forces beneath it. That search is a central task of physics. Far from Earth's surface, gravity is no longer constant. Its strength depends on distance. Newton's Universal Law of Gravitation captures this. Take two point-like objects of mass m1 and m2 separated by a distance r. The gravitational force between them points along the line joining them. It always pulls them together, and its magnitude falls off as the inverse square of that distance. Written as a vector, the force on object 2 is minus g times m1 m2 over r squared times the unit vector pointing from object 1 to object 2. That unit vector sets the direction along the line. The minus sign flips it around, so the force points back toward object 1, attraction. G is the gravitational constant 6.67 times 10 to the negative 11th in Newton meters squared per kilogram squared. It is the same for every pair of masses in the universe. Inverse square is a strong statement. Double the distance between two masses, and the force doesn't just halve, it drops to a quarter because 2 squared is 4. Triple the distance and it falls to a ninth. Move them 10 times as far apart and the pull shrinks to 1/100th of its original value. Gravity reaches across any distance and never truly vanishes, but it weakens fast. This same inverse square shape will return when we meet the electric force, a hint that nature reuses its mathematics. There's a subtle assumption hiding in that formula. The mass in the law of gravitation measures how strongly an object responds to gravity, call it gravitational mass. But mass also measures how strongly an object resists acceleration. Its inertial mass, fixed against the standard kilogram. These are logically different ideas. The principle of equivalence states they are identical. Gravitational mass equals inertial mass. Experiment confirms it to extraordinary precision. From here on, we assume it, and write both with a single symbol. Bring one object down near Earth's surface and something convenient happens. Over the modest range of everyday heights, the distance to Earth's center barely changes, so the gravitational force is nearly constant. Its magnitude is simply mass times g, m times g, where g is a positive constant, the local acceleration of a freely falling object. The international standard value adopted for a body falling in a vacuum is 9.80665 meters per second squared. But g is not one fixed number across the planet. Its true value drifts with latitude and elevation, and Helmert's equation pins it down. On screen, g equals a base value near 9.81 minus a term proportional to the cosine of twice the latitude, plus a small correction in that cosine squared, minus a term that subtracts gravity as you climb in elevation. Watch what the latitude does. At the equator, latitude 0, the cosine term is largest and the g comes out to about 9.78. At the poles, the cosine flips sign, adding instead of subtracting, and g rises to about 9.83. At 42 degrees latitude at sea level, the equation gives 9.80345 meters per second squared. And there, the standard kilogram weighs 9.80345 newtons. Every object at that spot falls with that same acceleration. Why is the pole stronger than the equator? Two effects, both from the Earth's spin. First, rotation throws objects outward slightly, an apparent outward force that offsets a little of gravity, strongest at the equator, zero at the poles. Second, that same spin has flattened the planet. Its radius is larger at the equator than at the poles by about 21 kilometers, so equatorial objects sit farther from the center and feel a weaker pull. Gravity dips locally too, with the rock and water beneath your feet. Variations real enough to guide oil prospecting, map the water table, and steer submerged submarines. Hunting anomalies in G has even fueled searches for a proposed fifth force. We started with a spring and asked what force truly lies beneath it. Following that question led us to gravity, the first of nature's fundamental forces, an attractive, inverse square pull between any two masses, tied to inertia by the equivalence principle, and calibrated at Earth's surface by G. The very same question about the spring's atoms pointed at electric charge. That is where we head next, the electric force and Coulomb's law. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.